Hey everyone, my name is Heppert and I now want to present our recent work CARTO, Category in Joint Agnostic Reconstruction of Articulate Objects. This is joint work with collaborators from Georgia Tech, Kyoto Research Institute and Stanford University, and is presented at CVPR 2023. If you think about articulate objects, they are present in abundance in our homes. In almost every household one will find refrigerators, ovens, cabinets, etc. And thus, detecting and reconstructing articulate objects is an important skill useful for many downstream applications, for example in robotics or augmented reality. For instance, imagine a robot is entering a new kitchen it has never seen before, and it should perform some task involving articulate objects. To safely interact with these objects, the robot needs to reason about the layout and the potential movement of all objects in the scene to make sure it does not collide with any. In the shown example here, CARTO, for instance, can reason about the opening direction of the cabinet door. Another application in robotics could be loading this reconstruction in a simulator and let the robot safely learn interaction policy for that door. Another application could be in augmented reality, where we can use reconstruction of articulate objects to reason about potential occlusions. Here, for instance, if we want to place a virtual cake in our oven, we can calculate the occlusion by our door and render the cake more spatially realistic in the image. To tackle this problem of articulate object detection reconstruction, we present CARTO, a single-shot pipeline. The input to CARTO is a stereo RGB image pair, for instance recorded with a Z2 camera. We then use a stereo encoder based on SimNet by Kollar et al. That extracts a feature pyramid which is fed to multiple output heads. While not directly needed for further inference, CARTO uses a depth fed during training to guide the network towards 3D geometry. As an additionally auxiliary output, we predict 3D bounding boxes and a segmentation mask. Now, more importantly, we predict a category-independent heat map over all articulate objects in the image. Here, the closer we are to the 2D spatial center of an object, the higher the likelihood. Second, for each pixel we predict a latent code that captures the shape as well as the articulation state of the object, where the articulation state consists of the actual joint state and joint type. Last, for each pixel we predict the pose of the object at that pixel. By now applying maximum suppression on the heat map and performing peak detection, we retrieve pixel image indices which we can use to index our code and pose map to retrieve the code and pose of each detected object. We will first use the predicted latent code to decode the articulation state of the object, namely the joint state and the joint type. The code also serves as input to a geometry decoder that reconstructs the object in the canonical frame. We do the decoding step for all detected peaks, here in this example for both objects. Lastly, we create a pose map to get a pose for each object, which is then used to place the reconstructed objects in the camera frame. To train CARTO, we first train the decoders on a set of instances taken from partner mobility. To train the CARTO's different output heads, we proceed to generate synthetic kitchen environments with ground truth labels. We evaluate CARTO quantitatively and qualitatively on a synthetic dataset generated with the same procedural generator. But for the evaluation set, we select optic instances never seen during training, either for the object-centric decoder nor for the full pipeline. And thus, CARTO is able to generalize to new object instances in the same domain. Here, in this example on the top left, you can see a predicted heat map, for which CARTO correctly identified both articulate objects. On the right of it, in B, we visualize the predicted poses as well as the bounding boxes derived from the reconstruction. C shows the auxiliary depth predicted by CARTO. The bottom row on the left, D shows a visualization of the full scene reconstruction. And lastly, as we decouple the shape code from the joint code, we can vary the joint code to reconstruct the same object instance but for a varying joint state, shown in E. By building up SimNet by Kollar et al., we are able to generalize to real-world instances without any fine-tuning. Here you can see the inference results of the very same model as before, but performing inference on a real-world scene. Again, CARTO correctly detects the articulate objects, reconstructs it, and places it in the camera frame. We also release more than 200 real-world images annotated with 3D bounding boxes of articulate objects. This wraps up the short presentation. Thank you for your attention. A great thanks to all of my great collaborators. And if you're interested in CARTO or have more questions, please check out our website linked through this QR code or just send an email.